Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone, and thank you for being here today. Before I begin, let me briefly introduce the topic that my team and I have been working on over the past several months. In the field of aircraft engineering, safety and structural reliability are always our top priorities. Even a small crack, if left undetected, can lead to serious consequences. This reality has motivated us to explore how early crack from and grow in one of the most important structural components of an aircraft wing. Today, I will present our research title Prediction of Early Fatigue Crack Growth in the PSI of our wing skin of the N-2XX aircraft using T-crack. This work was conducted by myself, Edi Suryono, from Mechanical Engineering Sekolah Tinggi Teknologi Warga Surakarta, along with Renald Rahadian Yosanto from Mechanical Engineering Sekolah Tinggi Teknologi Warga Surakarta. Next, Fikni from Mechanical Engineering Structural Design and Analysis from PTDI PT Dirgantara Indonesia, and Mr. Chamim from Mechanical Engineering Sekolah Tinggi Teknologi Warga Surakarta. My agendas for presentation. First, background to the problem. To start, let me give you a brief background of why this study is important. Aircraft structure experience repetitive loads during a free flight, during takeoff, landing, turbulence, or even routine maneuver. Over time, this load creates fatigue, and fatigue can initiate tiny crack in structural components. One of the most critical components is the principal structure element, or PSI, located in the lower wing skin of the N-2XX aircraft. The section carries the main bending loads generated by aerodynamic force. Because of the stress concentrates in this region, small cracks can form and grow gradually. If these cracks continue to grow unnoticed, they can reach a dangerous length and might lead to structural failure. Previous studies by Reimer and Asia emphasized that geometric feature and stress distribution greatly influence crack growth behavior. This inspired us to take a closer look, not only to understand the crack pattern, but also to support better maintenance planning. With this background in mind, our study aims to answer a key question: how do geometric factor and stress concentration affect early crack growth in the lower wing skin structure? In particular, we compare two different regions which we refer to as skin A and skin B. By understanding this difference, we hope to contribute to safer flight operation through better prediction of inspection interval and service life estimation. Our study also linked with the latest guidelines from regulatory bodies such as the FEI and PTDI regarding structural inspection for aging aircraft. To conduct our analysis, we use a software tool called the Greg. For those who might not be familiar with it, the Greg is a program specifically designed to predict fatigue crack growth by considering real operational loads. The software requires several key inputs. One, material properties of AL 20 and 24 P 351. 2. Flag spectrum data. 3. The B factor or beta factor. As highlighted by Asia, the beta factor is critical because even slight change in geometry can significantly accelerate or slow down crack growth. With all this input, the crack generate a prediction of how crack develop over time. Our methodology combines both VM, VM and the crack simulation. First, we analyze three potential crack types: corner crack, choke crack, and eccentric crack. These crack types were selected based on previous studies from Zhang, Kulmer, and Chen, who examined similar conditions in lower wing structure. When they use film, the test determined the stress distribution across the wing skin. FEM also asks to visual which are experience the highest stress and are therefore more likely to initiate crack. The stress result from FEM were when the then input into the crack to simulate crack propagation under real flight condition. Let's move on the to the results, starting with skin A. Skin A displays the stack crack growth pattern. In the first stack, from flag 1 to 600, the crack grows in a linear and predictable manner with an average increase of 4.758 millimeters. However, once it reaches around 600 flag, we see a drastic change. To grow the rate jump from 1.642% to over 20%, which is a sign of rapidly acceleration damage. This exponential trend is alarming because it indicates that the structure is moving towards a critical failure condition. In other words, once the crack reaches a certain size, it grows very quickly and becomes difficult to control through regular maintenance interval. Skin B. Skin B shows a much more stable behavior. Throughout the simulation period up to 1,200 flags, the crack grows linearly with an average growth of 6.566 millimeter and only a slight increase in the growth rate around 1.18%. From this result, we can draw several important insights. Skin A, skin A is more vulnerable due to its resistance into rapid exponential crack growth. Skin B is more resistant and shows a severe linear crack progression. This finding has practical implication. Ultimately, understanding this crack growth behavior helps us ensure the long-term reliability and safety of aircraft structure. To summarize, skin A shows a two-pass crack growth pattern with a dangerous exponential increase after 600 flights. Skin B shows a safer linear crack growth pattern, indicating better fatigue performance. Therefore, special attention must be given to skin A in terms of design, monitoring, and inspection frequency. This research highlights the importance of combining FEM and crack simulation to support maintenance planning, structural evaluation, and aircraft safety assessment. Once again, thank you all for your time and attention. I hope this presentation has provided a clear understanding of our study and why it is important for ensuring aircraft structural safety. Bye bye, thank you.